Welcome back to part 2 of Pre-Calc Notes 9.1. We left off talking about factorial notation, and we were on this problem here. Remember that factorial means, for example, if it was 5, factorial it's 5 times 4 times 3 times 2 times 1. So it's always 1 less than the previous integer, all the way down to just 1. So when you have variables involved in it, you just keep taking 1 away from each of those. So if we were to solve this problem here, we would do n plus 2. 1 less than n plus 2, if I take 1 away from there, would be n plus 1. And 1 less than n plus 1 would just be n. Now the reason I'm going to stop at n factorial and not do then n minus 1 and n minus 2 and so on is because the denominator down here is n factorial. So what will happen now is what's in the numerator and what's in the denominator, if they're the same, they'll cancel out. And I'll be left over with n plus 2 times n plus 1 as my final answer. So you're applying the same process, just like when we did this one. We did 12 times 11 times 10. We did 1 less each time, and we got it to cancel out with the tens. It looks a lot more complicated with this one because of the fact that I have variables involved. But if we subtract 1 from 2, we get 1. If we subtract 1 from 1, we get 0, and that's why there's just an n there, n plus 0. So that's the same process that we are working on. So the next problem that we want to deal with now is something called summation notation, or sigma notation. You're going to see this, it looks like an E. This is the Greek letter sigma, and it stands for sum. So if you have a problem like this, where it says k equals 1, and then you see the sigma sign and a 3, what it wants you to do is plug into here a k equal to 1, 2, and 3. So this 1 down here is where we start, and this 3 up here is where we stop. And we just plug it in for the variable then. And because it says the summation, or the sigma, we add those all up. So it will kind of look like this. So if I plug a 1 in for the k here, it would be 2 times 1 plus 1. If I plug a 2 in, it would be 2 times 2 plus 1. And if I plug a 3 in, 2 times 3 plus 1. But because of the summation sign, it means then we have to add those results together. So this would give me a 3, this would give me a 5, this would give me a 7. When I add that up, I get 15. So again, the bottom number here is our starting number, our top number here is our stopping number, and we just plug those in, add up the results all the way for this problem from 1 to 3. Now this time they give us the variable n instead of a k. So for this one I want to find when n is equal to 2 plus what n is equal to 3, 4, 5, and 6. So I'm going to start at 2. I'm going to plug in a 2. Then I'm going to plug in a 3, a 4, a 5, and a 6. And again, I'm going to add those all together because of the sigma sign, or the summation notation there. And so doing that, I'm going to get 8 plus 12 plus 16 plus 20 plus 24. And that adds up to be 80. There actually is a faster method to doing this one. I could look at this as saying it's 4 times the summation of n when I go from n equals 2 to a 6 up here. So what that really means is I would do 4 times the sum of 2 plus 3 plus 4 plus 5 plus 6. That's a little bit faster. So when you've got multiplication here and you're multiplying it just by n here, you could take this 4 and bring it to the outside, figure out what 2 plus 3 plus 4 plus 5 plus 6 is, and that ends up being 20, and then times that answer by 4. And you get 80 either way. A lot of students prefer this method just because you don't have to remember when you can break these up and put the 4 on the outside. So either method will work, it's just one tends to be a little bit faster than the other. So on the topic of breaking up the summation notation, you could look at this problem as opposed to one summation from k equals 1 to k equals 2 and k equals 3. like we did previously, you could look at this as breaking it up to say it's the sum from 1 to 3 of whatever 2k is, plus then the sum of from 1 to 3 of 1. So you could break that up and get your answer. I think for a problem like this, that would take a lot longer to do, because you'd have to do 2 times 1 plus 2 times 2 plus 2 times 3, and then you'd have to say, okay, for k of 1 you'd have to do plus 1, for k of equal to 2 you'd have to add another 1, and for k equal to 3 you'd have to add another 3. And you'd get 15 like we did on the previous couple problems there, but that way I think is going to be much longer than if you were to just to do it like we did in the previous examples there. So you can break summation notation up. I don't think that it's wise to do that for this problem though. Now sometimes summation notation, it won't always ask you to go from 1 to a certain number, it may ask you to go from 0 to a certain number. So for this one we'd have to go from 0, 1, 2, and 3. So doing that we would have 2 raised to the 0 power plus 2 raised to the first power plus 2 raised to the second power and 2 raised to the third power. And doing this we would get 2 to the 0 is 1, then 2, then 4, and 8. And so our answer would be 15 again. With this next one here, we're going from 1 to 4 of 3. So we have to do k equals 1, 2, 3, and 4. And there's no k value to plug a 1, 2, a 3, and a 4 into. So all you're basically doing is you're adding 3 up for each of these numbers. And since there's 4 of them, k is 1, 2, 3, and 4, that makes 4. You just add 3 plus 3 plus 3 plus 3, and you get 12. So when there are no values to plug the k into, like here there's a k, here there was a k, but in this problem there are no values that you can plug k into, you just add that number up as many times as you have the k's. In this case you had 4 k's from 1 to 4. Alright, for this next one we're going from k of 0 to k of 8, so we want to do k equals 0, 1, 2, 3, a 4, a 5, a 6, and a 7, and an 8. So I'm not going to write out k equals that every single time. I'm just going to list those all out so I know how many times I have to do this. And then I'll do 1 over 0 factorial, plus 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, plus 1 over 4 factorial, plus 1 over 5 factorial, plus 1 over 6 factorial, plus 1 over 7 factorial, plus 1 over 8 factorial. So this is going to be something that we obviously are going to want to add, put into our calculator. And when we put it into our calculator, we're going to want to make sure we use the factorial button and we tell the calculator that these are fractions by putting them all in parentheses. So I invite you to pause the video and type these all into your calculator. Then play the video again and see if you're going to get the same answer that I come up with. So again, please pause the video and try this and see if you can get the same answer. When I did it, I got a decimal 2.71828 as our answer. So hopefully you did too. If you didn't, I would suggest that you try to re-enter it in and see if you can get the same answer. Alright, the last one is a little bit different because it's going from k equals 0 all the way up to infinity. So there's no way that I can actually type every single one of these in to get an answer. So what I want to do is I want to see what this number is approaching. So that's what I'm going to try to look at. This number is going to be approaching what? By looking at a pattern. So I have to do a few of these. And I have to do as many as it takes for me to see the pattern. So let's just start off with a few of them. So I would do 1 over 2 raised to the 0 power, plus 1 over 2 raised to the first, plus 1 over 2 raised to the second, plus 1 over 2 raised to the third, plus 1 over 2 raised to the fourth. And I could continue that. But I'm going to see what this equals here and see if I can identify the pattern. And as you're doing this, it's probably a good idea to type it in your calculator as you go. Not all at once, so I'm going to do 1 divided by 2 raised to the 0, and I get 1. Then I'm going to add to that half, and then I'm going to add to that a quarter, and then it looks like an 1/8 and a 1/16. So it looks like what I'm doing is I'm adding half of the previous number every single time. When I add all of these up, take a second to type that in my calculator. I end up getting 1.9375. Okay? So the next thing I'm going to do, the next process, if I add one more in here, k equals 4, or 5 I mean, would be add 1 over 2 to the 5th. Well, that's 1 over 32. So if I add 1 over 32 to this, I get 1.96875. The next one would be, if I add 6, it would be 1 over 2 to the 6th power. Well, 2 to the 6th power is 64. So if I add to this 1 over 64, plus 1 over 64, I get 1.98. So it looks like what's happening, because every time I'm doing this, I'm adding less and less numbers to it than the previous time. So I'm adding half and fourth, so that's less than 1/2. 1/4 is less, or 1/8 is less than 1/4. 1/16 is less than 1/8. So I keep adding less and less, and eventually what's going to happen here is my problem is going to get as close as possible to 2. It goes from 1.93 to 1.96 to 1.98. So the answer to this problem is 2, because that's what it's going to be approaching. I can't possibly list every single number because it's going to infinity, but what I want to do is do enough of them so I can start to see the pattern. You know, after I did about 4 of them, I got 1.9375. Add another one to that, I got 1.96. The next one would be 1.98. I could add one more if I wanted. If I added 1 divided by 2 raised to the 7th, the next one would give me 1.992185. So you'll see that I'm getting eventually closer and closer and closer to 2, but I'm never going to go over that. If you're not sure about that, keep going. Keep putting 1 over 2 raised to the 8th, 1 over 2 raised to the 9th, 1 over 2 raised to the 10th. You'll never get to a number over 2 here. So this one, when it's an infinity, you have to just see what is approaching, what the pattern is here.